My pleasure to introduce you all to Anne Green. So Anne Green is a professor at the University of Nottingham in the UK. So she's an expert on things to do with cosmology, astroparticle physics, but probably principally topics related to dark matter, and in particular primordial black holes as a dark matter candidate, which is what she's going to talk to us today about. So Anne also has the honor, I guess, of having been my PhD supervisor. So it's my pleasure to introduce you to her, and I'm sure she's going to give a great talk. So yeah, I'll leave you with Anne.
Okay, great, thanks. So as Kieran said, I'm going to talk about primordial black holes as a dark matter candidate. And this talk is based on a review I've recently written with another former PhD student of mine, Bradley Kavanagh, where we attempted to sort of do an overview from a slightly critical point of view of primordial black holes as a dark matter candidate. So to start with, I'm going to talk about the motivation for thinking about this. I'm then going to talk about the formation of primordial black holes, and then finally I'm going to talk about constraints on their abundance. And if time permits, I'll talk briefly about some work that I've done myself on microlensing constraints on primordial black holes. Why are my slides not now advancing where they did back there? So I won't go into great detail about the observational evidence for dark matter, but we're now at a point where there is really very convincing evidence for non-baryonic cold dark matter from a wide range of observations ranging from individual galaxy rotation curves through galaxy clusters to large-scale structure and the CMB. Although the caveat there is that all of this assumes that our understanding of gravity is correct. I'm not aware of any theory that really can do all of these observations without dark matter, but that's not to say that somebody isn't going to come up with something which could in the future. So to really confirm that dark matter exists, we want to actually detect what it is. So primordial black holes are black holes that form in the early universe from large overdensities. And they form before nucleosynthesis, which means that they are non-baryonic. So that ticks one of the boxes for our dark matter candidate. Dark matter also needs to be stable on cosmological timescales. Famously, primordial black holes are thought to evaporate via Hawking radiation. However, their lifetime is longer than the age of the universe if their mass is greater than about 10 to the 15 grams. So primordial black holes more massive than 10 to the 15 grams are then a dark matter candidate. For context, 10 to the 15 grams is about the size of a large mountain, which gives me an excuse to show you a gratuitous holiday photo of Mount Everest. Primordial black holes are very different from the other dark matter candidates that are typically considered, for instance, WIMPs, axions, stereo neutrinos, in that they're not a new particle. Sometimes people say that that means that they have the advantage that they don't require new physics, and I've myself in the past have said that. However, I don't think it's strictly speaking true. As we'll see in a moment, you typically need some sort of beyond the standard model physics to produce the large overdensities that are needed to form them. It's been realised that primordial black holes are a dark matter candidate going right the way back to when they were first proposed in the 1970s. What's led to a surge of interest over the last 3-4 years is the detection by LIGO Virgo of gravitational waves from mergers of tens of solar mass black holes. Now, I'm not an expert on astrophysical black holes. My understanding is that these big black holes and then binaries made of them could have been formed via various astrophysical processes, although there are challenges. However, what was unexpected was having such a large population of them that you would see these mergers. And so there was a sort of wave of papers in early 2016. Could primordial black holes be the cold dark matter and also potentially the source of these gravitational wave events? So to have a primordial black hole form in the early universe, you need a large overdensity. There are various ways of doing this, for instance, bubble collisions, cosmic string loops. But the most well-studied mechanism is the collapse of large density perturbations during radiation domination. And these are the same density perturbations that on much larger scales form galaxies and galaxy clusters, but on smaller scales, and as we'll see in a moment, with much larger amplitude. And if the amplitude is sufficiently large at horizon entry, then gravity can overcome the pressure forces which are resisting collapse, and you get a black hole formed with mass roughly equal to the mass within the horizon at that time. The essential analysis of the requirements and resulting black hole mass dates back to Bernard Carr in the 1970s. The key quantity is the density contrast, i.e. the relative overdensity of a particular region. And he showed that a primordial black hole will form if that quantity is bigger than some critical value, which is roughly equal to the equation of state parameter W, which is a third during radiation domination. And then in that case, you get a primordial black hole formed with mass, which is roughly equal to the horizon mass. And for context, this is how the horizon mass depends on time t. So the lightest primordial black holes that survive to the present day without evaporating, the 10 to the 15 grams, they will be formed a tiny fraction of a second after the Big Bang, whereas solar mass black holes will be formed at around the time of the QCD epoch. There's been a lot of work in particular over the last few years at refining the criteria for PBH formation. And it's been found that in fact, the threshold depends on the shape of the perturbation from which the black hole is forming, and hence the primordial power spectrum. However, as a benchmark calculation, this is in fact sort of really not too bad at all. The quantity we're interested in is what's called the initial primordial black hole mass fraction, i.e. the fraction of the universe initially in regions that are overdense enough to form primordial black holes. It's called beta, and to calculate it, we take the probability of the density contrast on the relevant scale and integrate it from the threshold for PBH formation up to infinity. So for a simple calculation, assuming a Gaussian probability distribution, and I'll come back to that assumption in a moment, what you get out is that beta is a complementary error function, and this quantity sigma here is the mass variance. For practical purposes, it's essentially the typical size of the fluctuations. So this diagram tries to illustrate this. In blue, we've got the probability distribution. Sigma is the width of the distribution. Here's the threshold delta C, so I'm assuming the simple value of a third, and the primordial black holes form from these large rare fluctuations out in the tail of the distribution. As we'll see in a moment though, beta, the initial mass fraction, has to be very small. So in fact, this width is very, very small, and only a tiny fraction of the distribution is up here in the tail. So then let's have a look at the initial abundance of primordial black holes. And the key thing is that because they're matter, their density dilutes as a to the -3, whereas the density of radiation dilutes as a to the -4. And that means that during radiation domination, the fraction of the universe that's in the form of primordial black holes actually grows proportional to the scale factor A. So here I've drawn a plot of the log of the density relative to the total energy density. Early on, we have radiation domination, and then later on, matter domination. And so radiation is initially dominant, and the primordial black holes are extremely subdominant. However, the fraction of the total density they make up increases with the scale factor during radiation domination and then becomes constant during matter domination. And so we can work our way backwards from a particular fraction of the dark matter being in the form of primordial black holes today, F, and work out what the corresponding initial mass fraction has to be. And very roughly, you get an expression of this form here. And so what we're seeing is that, say, for instance, solar mass black holes, to make up all of the dark matter, the initial mass fraction of primordial black holes has to be tiny, 10 to the minus 9. So not exactly 0, but very, very small. And lighter primordial black holes form earlier, so you go back further, and hence the initial mass fraction required gets even smaller. On CMB, cosmological scales, we've measured the amplitude of the primordial perturbations, and it's 10 to the minus 5. So we can already do a quick calculation of the abundance of primordial black holes you would get if the amplitude of the perturbations was scale invariant, i.e. the same on all scales. So taking the simple expression for beta and inserting a threshold of order unity and sigma, the typical size being 10 to the minus 5, you get the complementary error function of 10 to the 5, which is e to the minus 10 to the 10. So what we're seeing is if the perturbations on small scales have the same amplitude as on cosmological scales, the number of primordial black holes you would form will be completely negligible. Flipping it on its head, if you want to have an interesting number of primordial black holes today, then you require the amplitude of the perturbations on small scales to be several orders of magnitude smaller. So this plot here is a plot of the primordial power spectrum, which is loosely equal to the square of the amplitude of the perturbations as a function of co-moving wave number k, or equivalently the horizon mass, which is then roughly equal to the mass of the primordial black holes that form. So on cosmological scales over on the left, this has been very accurately measured by Planck. There's also a slightly less accurate measurement on slightly smaller scales from large scale structure. There's weaker constraints on intermediate scales from CMB spectral distortions, and then on smaller scales there are indirect constraints from induced gravitational waves, which I'll talk about later on. The dashed lines are potential constraints from future observations, and then this black line is the required amplitude to form an interesting number of primordial black holes. So what we're seeing is that to make primordial black holes, the amplitude of the power spectrum has to grow significantly from its measured value on cosmological scales. And this dotted line here shows the steepest growth that can be obtained in single field inflation models, which I'll talk about a little more in a moment. So before we do that, though, I should mention a few deviations from the simple scenario. So in the simple scenario, the primordial black holes formed at a specific time all have the same mass, roughly equal to the horizon mass. In fact, there is a phenomenon called critical collapse that applies to black hole formation in general, and Niemeyer and Jadamczyk were the first people to study this in the context of primordial black holes. And in fact, the mass of a black hole formed, it does depend on the horizon mass, but it's also proportional to the size of the fluctuation from which the black hole forms, in particular in this power law form here, in terms of how big the fluctuation actually is relative to the critical threshold. And there have been numerical simulations that have sort of verified this power law scaling over a huge range of values of delta. So the upshot is that still the typical mass of the black holes is roughly equal to the horizon mass, but there is a long tail of lighter black holes formed at any given time. So the key thing here is that even if all of the black holes form at the same time, they don't have the same mass, i.e. the mass function isn't a delta function. Next up is the assumption of non-Gaussianity. And since the primordial black holes are formed from rare large density fluctuations, any changes in the shape of the tail of the probability distribution, i.e. non-Gaussianity, will significantly affect the primordial black hole abundance. And again, there's been lots of work on this going right the way back to the 1990s, but then again, much more recently. And in fact, even if the primordial curvature perturbations are exactly Gaussian, the relationship between the curvature perturbations and the density perturbations is non-linear. So large density perturbations are inevitably non-Gaussian. However, unfortunately, it's then very difficult to do calculations for specific models. This paper here lays out a framework for doing it, but it's a highly non-trivial calculation. Another potentially extremely important issue, as we'll see later on when we come to looking at constraints, is clustering of primordial black holes. And there's been a lot of backing and forthing on this over the last few years. Initially, it was perhaps thought that primordial black holes would be clustered right from the moment of formation. That's now been shown not to be the case. However, if they make up a large fraction of the dark matter, you will get clusters of primordial black holes formed shortly after matter radiation and equality. And so you can see that sort of structure formation with a large component of primordial black holes looks like it's going to look somewhat different, but it's not possible to sort of run simulations looking into this right the way up to the present day. It's been done up to a redshift of about 100, but the open question is then what happens to these clusters between then and the present day. So we need something to generate density perturbations in general, and specifically large ones to form primordial black holes. So I'll sort of very briefly recap inflation. This is a postulated period of accelerated expansion in the very early universe, proposed to solve various problems with the standard Big Bang model. It's driven typically by a slowly rolling scalar field, and quantum fluctuations in that scalar field then generate density perturbations. And the scale dependence of the density perturbations depends on the shape of the potential. And so here we have a sort of cartoon of a simple model. The field slowly rolls along its potential, inflation happens. At some point, the potential gets too steep to support inflation, and then eventually we have the field oscillating around a minimum, decaying, reheating, and producing the standard Big Bang. So large-scale structure in the CMB correspond to a relatively small region of the potential some way away from the end of inflation, whereas large PBH forming fluctuations could potentially be produced over a much larger range of scales. In the slow roll approximation, where the field is evolving slowly, we have this simple expression for the typical amplitude of the perturbations, and it's inversely proportional to the slope of the potential. So naively, at least, if you want to make large fluctuations, you need to make the slope of the potential very small, i.e. make it very, very flat. However, there's a huge caveat here that once you get slope tending towards zero, you get into a regime of what's called ultra slow roll. And then this simple expression is in fact not valid. There are many, many, many inflation models in general, and even though the subset of them that produces large perturbations is not huge, nonetheless we end up with a large number of different models. I won't attempt to even talk about all of them. I'll just give you a couple of sort of characteristic examples. Now, the first thing that people have sort of looked at in particular recently is what you can do in a model with a single field. And it turns out to get sufficiently large perturbations, you have to fine-tune the shape of the potential. And in particular, what you need to do is have a form looking something like this, where you have a region here which produces the observed perturbations on cosmological scales, a steepening here so that inflation ends, and then a feature somewhere in between with position located to match the mass of the primordial black holes you want to form, where you have this local minimum followed by a sort of small bump so that you slow the field down so it goes through here with reduced speed. And the power spectrum produced by this fine-tuned model on the left is this red line here, where you see indeed you fit the measurements on large scales, and then you get a bump going up to the required abundance down here. You can also look at multi-field models, and the classical model in which primordial black hole formation has been studied historically is hybrid inflation. So in hybrid inflation, you have two fields and a potential that looks something like this. Initially, inflation is driven as one of the fields slowly evolves along here, but at some point you get this transition so that this is no longer the minimum. Instead, you have two minimum, and the field transitions to one of them in any particular region. Inflation ends, and then you get reheating. And depending on the details of this transition, you can potentially get large fluctuations formed at the transition, or you can even get a second period of inflation. And this then is what you get for the primordial power spectrum in the case where you get this transition takes a little while, and you get a peak which reaches the required abundance to form primordial black holes. And this, in this case, this peak is really rather broad. So again, this would lead to some spread in the masses of primordial black holes formed. And as I mentioned before, there's then a long list of other models where you could produce large primordial black hole forming fluctuations. So now, having looked at how we can form primordial black holes, let's look at the abundance on their the constraints on their abundance. And while I've emphasized that we expect the mass function to have some width, initially all these constraints assume a delta function mass function, and I'll come back to applying them to broader distributions at the end. So first up, we're going to have a look at microlensing constraints, and these happen when a compact object passes the line of sight between us and some background object, which could be a star, a supernovae, or a quasar. So the classical way of searching for compact object dark matter in the Milky Way's halo is stellar microlensing. And so here I've attempted to draw a cartoon of this. We're sat in the disk of the Milky Way, and we can observe this LMC and SMC, this large and small Magellanic Clouds, which are satellite galaxies of the Milky Way. And microlensing occurs when a compact object passes the line of sight between us and the Magellanic Clouds. So this is gravitational lensing, but where the separation of the images formed is of order microarc seconds. So instead of seeing separate images, what you see is a temporary brightening of a sort of particular individual star. And this is an image here, well, data here from a particular microlensing event observed by the EROS collaboration in the small Magellanic Clouds. And what allows you to sort of discriminate microlensing from other variations in the brightness of stars is that the brightening is achromatic, the same in all colours. So there were sort of various collaborations trying to do this back in the 1990s. What I'm going to show you here are the EROS collaboration's constraints on the fraction of dark matter in compact objects. And so these constraints are going down from solar mass through to planetary masses, and we're seeing that the compact objects in this mass range can't make up more than tens of % of the dark matter. Otherwise, we would have seen lots more microlensing events than were observed. And the Macho collaboration, they did see more events than you might have expected from stellar populations, but it turns out that actually part of what they were doing was discovering supernovae and background galaxies and weird types of repeating variable stars that nobody'd seen before. But in the region above 3 solar masses, the Macho collaboration have very similar constraints to EROS. More recently, people have done the same sort of observations on stars in M31, the nearest galaxy to the Milky Way. The duration of the microlensing event depends on the mass. The more massive, the longer the event. And so they did higher cadence observations. So they were sensitive to lighter compact objects. And again, the fact that they didn't see any allowed them to place much sort of tighter constraints down to % level on the abundance of lighter compact objects. As with many primordial black hole related things, there's been quite a lot of backing and forthing on these constraints over the last few years. And actually what has been realised is we're getting into a regime where microlensing becomes a bit more complicated. And there are two things you need to take into account. Firstly, the size of the source stars. And secondly, we're getting to the point where the Schwarzschild radius of the black hole is comparable to the wavelength of the light that's being used for the observations. So we're getting to a regime where you have to use wave optics rather than geometric optics. And that leads to a reduction in the magnification. And in fact, then there's a limit below which you don't get any constraints because the events, you just can't see them. And there's also been revision in the constraints from subtleties related to the fact that you need to be careful that only very large bright stars are bright enough for you to then be able to observe microlensing. You can also look at stars in the galactic bulge, and in that case, we know there's going to be lots of microlensing events due to other stars. And what's been seen is typically consistent with what you expect from the stars we know exist, apart from 6 ultra-short events with durations of a fraction of a day. So this on the left is the constraints in red that you get if you assume there's no microlensing by primordial black holes or other compact objects. So again, we're seeing sort of getting down to percent level constraints in sort of the middle of the HSC and Eros macro constraints that we previously looked at. On the other hand, if you decide that these 6 ultra-short events are evidence for primordial black holes, this is the region of parameter space that you end up in. So a few percent of the Milky Way halo being in planetary mass compact objects. However, we expect that there are sort of free-floating planets, so to me at least, it would seem most likely that these ultra-short events are actually due to free-floating planets rather than primordial black holes. So moving on to different types of microlensing, and in these you can actually sort of probe the granularity of dark matter. And in particular, with type 1a supernovae, there's a distribution of lensing magnifications, and this would be changed in the sense that there would be a tail of high magnifications where a line of sight goes close to a compact object, but on the whole, most lines of sight would be demagnified relative to dark matter being smooth. And so there's been work by these guys which found this constraint in blue, down to a sort of smallish mass. It's roughly independent of mass, and it's that roughly less than 40% of the dark matter can be in the form of sort of solar, planetary and heavier mass compact objects. Although there has been some work arguing that perhaps these constraints are overly restrictive due to various things. There's also a very interesting event called Icarus, which actually I must admit I only became aware of when writing the review paper, and I ended up spending quite a few days trying to sort of understand what's going on here. So the key thing is that in galaxy clusters you get caustics, lines almost, where there's high magnification, and that allows you to see distant stars, things at a redshift of a few. If you then also have compact objects in your galaxy cluster, you can get additional spikes in the microlensing. However, if all of your dark matter is in compact objects, the granularity then means that the overall magnification is reduced. And so this is a sort of theoretical calculation of magnification. So you see a huge factor here. And the black line is what you get from smooth dark matter, and the red line is what you get if you have a significant population of microlenses. And my mouse has just disconnected itself. So the first event like this, which was actually observed serendipitously whilst people were doing observations, I think, of supernovae lensing, involved a star at a redshift of 1.5. And the constraint from this event named Icarus is that F has to be less than about 10%, with some uncertainty due to uncertainties, for instance, in sort of transverse velocities of things. I have another mouse though, and my other mouse is thankfully working. So Finally, another type of microlensing is similar. It's quasar microlensing, where you get multiple images of a quasar. And then if you have additional compact objects in your lens galaxy, you get variations in the brightness of these multiple images. So in this case, what's seen is consistent with about 20% of the mass in the lens galaxy being in the form of slightly subsolar compact objects. However, this is consistent with the compact objects that we know are there in the form of stars. So it's argued that there's very little room for additional dark compact objects. However, no one's actually yet published a constraint on their abundance. So putting all of the things I've just told you about together, we get these constraints on planetary and stellar mass compact objects from microlensing. And I should emphasize that this and all of the subsequent plots I'm going to show you were made by Bradley Kavanagh using his PBH bounds package, which you can find here. So at sort of low masses, we've got the tight HSC constraints, and then moving up through planetary and solar masses, we have microlensing constraints from stars, Ogle, Eros, Macho, and then the Icarus, and also the supernovae constraints. So what you're seeing is that sort of we've got constraints that rule out all of the dark matter being in the form of primordial black holes over a wide range of masses, modulo the assumption that the primordial black holes have a delta function mass function, and also that they're not clustered. So moving on, there are also dynamical constraints from the effects of the primordial black holes on dwarf galaxies and wide binary stars. So these are slightly heavier multiple solar mass black holes. In a dwarf galaxy, if you've got populations of things with multiple masses, you get energy exchanged between them to try and equalize the energy. And the net result is that if there are things heavier than stars, the stars get dynamically heated and puffed up. And there are constraints from the fact that we don't see that. With wide binaries, these are very weakly bound, and if they have repeated encounters with heavy compact objects, they'll be heated, their separations increased, and some fraction of them disrupted. So in this case, we're getting sort of tens of percent and tighter constraints out at tens or hundreds of solar masses. Next up, we'll have a look at constraints from the consequences of accretion onto primordial black holes. And these come in sort of two types. You can have it happening at relatively high redshifts, and the resulting radiation distorts the CMB anisotropies. In this case, there are some significant uncertainties in modelling the accretion. In particular, do you get a disk forming? You could also get accretion happening in the Milky Way today, and you would be, if there was a lot of primordial black holes, you'd be seeing anomalous X-ray and radio sources, which aren't seen. So in both of these cases, we're getting really very tight constraints sub% level from tens of solar masses up. Finally, we're coming back to the gravitational waves, and I understand that Bradley will be giving you a longer talk on this later in the autumn, and he is definitely the expert here. So it was realized back in the 1990s that primordial black hole binaries could form in the early universe, just from occasionally they'll be close enough together for that to happen. It turns out that if these binaries survive to the present day, then the number of mergers you would be getting would actually be orders of magnitude larger than the merger rate measured by LIGO. So in fact, the LIGO observations put a constraint on the abundance of primordial black holes. However, as I'm trying to emphasize here, this is a fairly big if. As I talked about earlier, primordial black hole clusters would form relatively early, and then the orbits of these primordial black hole binaries, you would expect them to be perturbed by encounters with other black holes in the cluster. And so this is very much a hot topic that's being worked on to work out, how reliable these constraints are. There are also comparable constraints not from observing individual mergers, but from the stochastic background of all mergers. And so here are the constraints as they currently stand, and we're getting down to around % level in the sort of solar mass and larger region. So far, we've seen constraints mainly on planetary mass and heavier black holes, but the mass of a primordial black hole can go right the way down to 10 to the 15 grams. So we'd really like some constraints on these lighter black holes. And something that people have looked at in the past is constraints on these asteroid mass primordial black holes from their interactions with stars. So if a primordial black hole passes, a small one passes through a star, it can be captured via dynamical friction. And then the star can be essentially accreted onto the primordial black hole and destroyed. And in some cases, if you have a primordial black hole going through a white dwarf, it can heat it and make it explode. So various constraints have been claimed. However, my understanding based on this paper here is that actually currently there are no constraints, but potentially there could be constraints in the future, for instance, from the survival of neutron stars in globular clusters. But this will only be the case if there are globular clusters that we know have dark matter halos, because to destroy neutron stars, you need an environment where the dark matter density is high, but the velocity dispersion is low. And in general, the standard law is that actually globular clusters are star clusters which don't have dark matter halos. And then from the point of view of destroying stars, it needs somebody to do the difficult problem of working out exactly what the signature we should be looking for is. Finally, going right the way down to the lightest black holes that haven't evaporated but have started evaporating, there are constraints from the products of that evaporation. And people have looked at a range of things: extragalactic gamma rays, MEV gamma rays, effects on the CMB during recombination, and positrons. And the constraints are all actually fairly similar. Going down to very light black holes, the constraints are very tight because they're chucking out a lot of stuff, and then these constraints sort of go away once you get to about 10 to the 17 grams. So putting all of the things that I've just told you together, here is a compilation of the tightest constraints. So on the left, at the very lightest black holes, which would survive to the present day, there are constraints from the fact they've started evaporating. We then have microlensing constraints going sort of through planetary masses, through stellar masses, and then constraints from gravitational waves, accretion onto the black holes, and dynamical constraints going up to heavier black holes. So, as I've emphasized, all of these constraints have some sort of uncertainty, but what we're seeing is there are sort of so many different constraints in the solar mass region. It seems hard for the dark matter to entirely be solar mass primordial black holes. Although the one big caveat here is clustering. And I'm not saying that clustering should be used as something to wave these constraints away, but it will clearly have a significant effect on some of them, and the details of that are yet to be worked out. We do have an open window down here for very light asteroid mass primordial black holes. But to some extent, this is because they're very hard to probe. People, if they lose their keys, say, they'll start looking for them under the lamppost because that's where you can see them. And this is the opposite of this. This is the dark region of parameter space that's really hard to probe. There are also some indirect constraints that I haven't showed you yet, and that's because these apply only to primordial black holes formed via the collapse of large density perturbations and not to ones formed via other mechanisms. If you have the large curvature or density perturbations that you need to produce primordial black holes, these perturbations act as a second order source for gravitational waves. And so therefore constraints on gravitational waves can be translated into constraints on the power spectrum of the primordial perturbations, and hence into constraints on the number of primordial black holes formed. And so currently there are constraints here from pulsar timing arrays, but there is potential in the future from SKA, LISA, and future gravitational wave observatories that there's going to be actually much tighter constraints on the primordial power spectrum that would really tightly probe primordial black holes formed via this mechanism across a really wide range of masses. So finally, I'll talk to you about the things that I've actually been up to over the last couple of years. So as I mentioned, all of the constraints I've talked about so far are usually calculated assuming a delta function mass function. However, in fact, we expect the primordial black holes to have a finite width mass function, both from critical collapse, the fact that you get a range of masses formed even at a single time, and then we expect the primordial power spectrum to have some width so that primordial black holes are formed over a range of times. You sometimes see plots like this where a extended mass function is plotted on the constraints, and that's just not really the thing you want to do. You can't really compare DFDM with constraints on F. And in particular, you have to be beware of double counting. So for instance, for the Eros constraints, this is telling us that we can have F being 0.2 if all of the compact objects are 5 solar masses, or F of 0.4 if they're all 10 solar masses. But if we spread them out, we can't have both. And so those constraints need to be recalculated. It turns out that for the models of inflation that people have typically looked at that can produce large PBH forming perturbations, the resulting mass function can be approximated quite well by a log normal distribution. So if you then recalculate your constraints for a log normal, you're getting closer to what would be realistic. So I looked at this specifically by recalculating the microlensing and dynamical constraints from scratch. There was then subsequent work by Bernard Carr and collaborators where they came up with a way of doing the recalculations not from scratch, but by taking the delta function constraints and translating them. And this is the results of their work. On the left, we have the constraints as they stood at the time they did this work on monochromatic delta function mass functions. And so some of these constraints have changed, for instance, the HSC microlensing, and others, for instance, femtolensing, which I didn't mention, and the constraints on stars, those have gone away. But nonetheless, the key thing here is that if you go to a log normal mass function, and here they've calculated the constraints for a particular fixed value of the width, these constraints get smeared out. So for instance, the HSC, the tightest point becomes a bit weaker, but it also gets smeared out into other masses. And so if you had gaps between constraints for a delta function mass function, potentially say here in the solar mass region, those gaps would get closed once you go to more realistic, broader mass functions. So finally, I'll come back to something that has been close to my heart for a long time. So I've spent a lot of the last 20 years working on WIMPs as a dark matter candidate. However, I started off during my PhD working on constraints on models of inflation, and in particular constraints from overproducing primordial black holes. And this was the late 1990s, where the Macho collaboration was seeing an excess of microlensing events. And so that led to a first burst of interest in primordial black holes as a dark matter candidate. So I moved from looking at primordial black hole constraints on inflation to looking at the microlensing possible evidence for dark matter. And one of the things I did back then was look at astrophysical uncertainties on these microlensing constraints. I then moved on to looking at astrophysical uncertainties on WIMP detection, but going around full circle, I then came back and had a look again at how the astrophysical uncertainties affect the current microlensing constraints on primordial black holes. And so this was a case of digging out my old code and dusting it off. It wasn't quite on punch cards, but there was some upgrading it from Fortran 77 that was required before I could run it. So what I did was I looked at what are called Evans's power law halo models. These are self-consistent halo models where the density and potential are consistent, and they allow for non-flat rotation curves. Now, these are not the most modern or realistic halo models, but they're traditionally used in microlensing studies, indeed even by the Macho collaboration themselves, since there are analytic expressions for the velocity distribution. And so what I was trying to do here was not come up with a single recalculation of the constraints, but to benchmark the range of the uncertainties. So here we have the rotation curve of the Milky Way. The black solid line is what you get for the standard halo model that's typically used in microlensing calculations. The dotted line is roughly the envelope of observational data. And then the red long dashed lines are two benchmark models that have traditionally been used in microlensing studies. The top one is what's called power law halo B, which has a very heavy halo and a rising rotation curve. And then the bottom one has a light halo. And they sort of lie at the extremes of what's possible. This then is the corresponding plots of the microlensing differential event rate, the number of events you would expect as a function of time, and plotted here if all of the halo is in one solar mass compact objects. And so this is what you expect for the standard halo model. And so what you see is if you look then at these other halo models, or if you change the local circular speed in the standard halo model, you change the number of events you're seeing, and then you also change the typical duration. This is how that affects the constraints on a delta function mass function as a function of mass. So the black line is the standard halo model, and then this is essentially the uncertainty you get if you look at these power law halo models. So how tight the constraints are doesn't vary too much, but what varies is the mass at which they stop applying. I've also put on here the constraints at that time, the dynamical constraints. And so what I was trying to ascertain here is, are the astrophysical uncertainties sufficient to open up a gap between these constraints? And the answer is that if you take the weakest version of the dynamical constraints and the weakest version of the microlensing constraints, then there is this tiny window of parameter space in between them, but you shouldn't do that. I also had a look at the constraints on extended mass functions, and in particular on the width of a log normal mass function with f equals 1. And in this somewhat complicated plot, what we're seeing is that microlensing constraints exclude the bottom left. And in particular, I've shaded here the weakest version of the microlensing constraints when you take into account astrophysical uncertainties. And the CMB and dynamical constraints exclude the top right. And again, I've shaded the weakest version of the constraints. So this tiny slither of parameter space might be allowed. Sigma equals 0 corresponds to a delta function mass function. So that's what we saw in the previous plot. And what we're actually seeing here is what I showed you before. In fact, when you go to extended mass functions, i.e. with sigma non-zero, this gap closes. That extended mass functions are collectively, when you consider multiple constraints, more tightly constrained. So, to summarise, going right the way back to the beginning, primordial black holes are black holes that can form in the early universe by various processes, but most commonly considered is the collapse of large density perturbations during radiation domination. However, to produce an interesting, i.e. non-negligible number of primordial black holes, the amplitude of the fluctuations has to be 3 orders of magnitude larger on the scales you want to form primordial black holes than on cosmological scales. This can be done in inflation modules, for instance, by having a feature in the potential or having multiple fields with particular properties. However, the key thing to emphasize is this is not a natural or generic thing that happens in all models. Theoretically, primordial black holes are expected to have an extended mass function because of critical collapse and also the width of the primordial power spectrum. However, accurate calculations of that mass function are to some extent an outstanding issue. And then probably more importantly, how those black holes cluster is a really big open problem. There are lots of constraints on the abundance of primordial black holes, from gravitational lensing, their dynamical effects, accretion, and other astrophysical processes. And if we take those constraints at face value, it appears that solar mass primordial black holes can't make up all of the dark matter, but lighter asteroid mass ones could. However, the caveat here is that clustering could significantly modify the constraints. That's still to be worked out. And then finally, if you're assuming a realistic mass function, the constraints you get are collectively tighter than the ones which are typically calculated for delta function mass functions. So if I had to summarize in one word, primordial black holes are currently a viable dark matter candidate. However, there are various challenges for forming an interesting number of them, and there is some important work to be done in working out their properties, their mass function and how they cluster, and then revisiting the constraints in light of those things. So that's it, thanks.
Great, thank you. So should we take some questions now, Fran? Who wants to go first? I guess I will start in that case. I'll let you think. There was one thing that that sort of surprised me when you showed it, and it was the supernovae lensing constraints, which looked like they were going flat up to high masses, which I didn't really get, because I thought the more, like the higher the mass of the black hole, the fewer you have around to make up a given F. So why do the constraints not sort of go up at some point?
That's a good question that I can't answer. So I think, so you're absolutely right. The more massive the black holes are, the lower the number density is. And there certainly will be a point at which these constraints have to go up. And it's surprising that it isn't before 10 to the 4. So all of these sort of, the stellar microlensing constraints, there is a very strong mass dependence. These other microlensing constraints, where in fact what you're really probing is the granularity of the dark matter, there is this sort of surprising property that they end up being roughly independent of mass, and the same is true of the Icarus constraint. But I must admit, I'm not an expert at on this type of microlensing, and I haven't gone into the guts of the calculations enough to understand the physics behind that. So bottom line, it's a good question that I don't know the answer to.
Oh, someone's written something in the chat. What seems to be the most plausible reason behind the formation of PBHs?
So, I mean, to be utterly honest, we don't know whether they form or not. But I think to my mind, probably the collapse of large density perturbations would be the most plausible mechanism, because we know density perturbations exist. They have to exist for galaxies and galaxy clusters to form. The challenge then is making those density perturbations large enough to produce an interesting number of primordial black holes. Although, as I mentioned in passing, there are a bunch of other mechanisms. Any process in the early universe which gives you large overdensities could potentially produce your primordial black hole. So phase transitions, which occur via the nucleation of bubbles, when those bubbles then collide, you could produce primordial black holes. Cosmic strings, you form networks with loops, those loops oscillate, and if they happen to all oscillate underneath the sort of Schwarzschild radius, you could get black holes forming. And then there's also been recent work by Alex Kosenko and collaborators looking at the fragmentation of scalar field condensates. So that there are various possibilities, but if I had to vote, I'd say the collapse of large density perturbations.
Are they in some sense kind of inevitable to exist, at least? Maybe not as even a decent fraction of dark matter, but people talk about axions, and even if axions aren't dark matter, they still kind of should exist if you believe in the solution to the strong CP problem. Is there a similar argument that you can make for primordial black holes if you believe inflation has to happen?
Right, so it probably comes down to what you think the primordial power spectrum of dense perturbations is doing. And so this sort of calculation I did here is for a scale invariant. So if this was just completely constant the whole way across. And there you get the fraction being e to the minus 10 to the 10. I haven't compared that with the size of the observational universe, but I think that would work out at it would be stochastic, but the probability would be that there would be no primordial black holes within the observable universe in that case. And in fact, as you may or may not know, on cosmological scales, the power spectrum is actually sort of decreasing. So if you extrapolate this, it goes down, 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 and the numbers will be even smaller. But for reasons which I probably shouldn't go into today, you shouldn't just extrapolate power laws. Slight tangent, but I'll mention it anyway. There's been some work done by Ruth Gregory and collaborators of weird stuff that could happen to the vacuum if you have primordial black holes in the universe, and the potential that you could just destroy the universe if there was only even one primordial black hole. And I think Chris Burns and one of his PhD students did some work on the resulting constraints on the power spectrum that would apply in that case. So the short answer to your question is that, in fact, I think it is entirely possible that the number of primordial black holes in the observable universe could be zero.
Mm.
Yeah, that's.
And I probably should interject, so that Bernard Carr would argue that there are, in fact, a whole slew of other interesting things that primordial black holes could do, even if they weren't the dark matter.
Of course, constraints from the vacuum stability depends on the Higgs potential, I guess. So
I'm not an expert on the details of that, but yes, without a doubt, there are complications there.
I think we'll have to encourage people to speak up. I think Bruce has hands, but
Yeah, there was one. I'll just read out the question that was put in the chat. Is there a way to resolve between primordial non-Gaussianity and the non-Gaussianity arising from the relation between delta and curvature perturbation from PBH constraints? I have to admit, I don't actually understand the question, but perhaps you do.
Okay, yeah, that's a technical one, and it alludes to something that I only mentioned in passing. So primordial non-Gaussianity is when
8 o'clock.
My phone is talking to me. Is when the primordial curvature perturbations are non-Gaussian. And then there is also this additional thing that's been realized recently, that even if the primordial curvature perturbations are Gaussian, the density perturbations will be non-Gaussian because of the nonlinear relationship between them. It's an excellent question, and I am not the person to ask it. That requires somebody who's more of an expert on perturbation theory than me. Yeah, good question, which I can't answer.
Bruce, do you want to go?
Yeah. So first of all, thank you for the terrific talk. The thing that caught my eye was the gap in the asteroid mass range, and you made some comments earlier on that there are difficult calculations about what the signatures would be, and that people are doing that, but they haven't been completed yet. I mean, I just attempted a very quick calculation of how many of these things there might be given some sort of asteroid-like mass, and if they saturate the dark matter, then these things are everywhere, and you would have something the size of a modest-sized asteroid just in the sort of the spherical volume out to Pluto's orbit. At any one, if it was a delta function in mass at that mass, there would be one on average inside the solar system under that definition at any one time. Now, I don't know what fraction of objects on, just sort of random orbits would end up colliding on the star or one of the planets, but that fraction must be relatively large. I mean, even if it's as small as 1 per mil, it would seem to generate a relatively large rate of this obviously spectacular thing happening. You know, accreting something the size of Jupiter or a star onto a black hole is a spectacular event by almost any definition.
I think such, even if they have the mass of a decent sized asteroid, they're very, very small, and that would still really inhibit how fast you can accrete onto them. So if they're not properly trapped inside Jupiter, they might just pass through, barely accreting anything.
Sorry, because of Eddington limit issues? Because, I mean, some of the...
Oh, they are very dense, you know, they're black holes.
Sure. So some of the work that was done for the limits that were done for LHC disaster scenarios and such must be able to be repurposed or some of that work must be able to be repurposed for these sort of limits, right?
So I think another part of the problem is that they're moving quite fast, a couple of 100 kilometers a second. So there's a really comprehensive paper by Bernard Carr and Mary Sakellariou that goes back to the 1990s, and they looked at every possible sort of observational constraint on compact objects in general. So I think those, if there was a signature of that nature, those guys would have probably picked it up. And so, I mean, there's various things where there is definitely lots of ongoing work going on. But in terms of it, sort of signatures of asteroids, mass objects and their interactions with stars, maybe there's stuff going on, but if there is, I don't know about it yet. So this is definitely a case where it's not so much, there is some refining of calculations to be done, but it's more a case, I think, where radical new ideas would be a useful thing. And I think just one thing to sort of emphasize, appealing to authority isn't a great idea, but one of the authors of this paper is Chris Hirata, and he's a superstar theoretical astrophysicist who I tend to trust what he says. So there are at least some very clever people who have been thinking sort of deeply about this.
Okay, but at least part of the answer is that these things would in general be moving very fast, and that complicates their ability to eat a larger object. They could end up just punching straight through it.
Precisely.
Okay. And I think Ulrich has dropped something into the chat. Yeah, fair enough. Okay. All right. Thank you very much.
I have another question. I've seen some papers on possible ways to stabilize black holes so they wouldn't be constrained by the evaporation time limits. But are there any other kinds of constraints on these smaller black holes if you manage to stabilize them?
Right. So, I mean, for the canonical sort of case where they evaporate, there are a bunch of constraints on lower mass primordial black holes and the consequences of their evaporation. But obviously, if you then get rid of evaporation, those constraints go away. Off the top of my head, you would then possibly be looking at these sort of indirect constraints that they could, go down. But in terms of constraints on the primordial black holes themselves, the even lighter ones would be even harder to detect than the asteroid mass ones by mechanisms other than their evaporation. So I'm not aware of anything.
Does anyone ever talk about like basically direct detection of primordial black holes at a certain mass, where you expect to see lots of, I don't know, people getting killed by being struck by black holes, or because eventually you get down to a certain mass and you're sort of into the realms of these like composite object sort of weird like nuggets and stuff. These sorts of dark matter candidates where people have come up with all sorts of weird basically direct constraints. Is that well into the regime where Hawking radiation should be playing a role, or I mean, do people talk about this at all?
Oh, that's a good point. I don't know, because the primordial black hole should be sort of, I don't know, leaking into those constraints somewhere, shouldn't they? Yeah, that's an interesting point. I don't know. It sounds like the sort of thing that Bernard would have thought, Carr would have thought about at some point, but...
There's a paper from last year on direct detection of primordial black hole relics as dark matter by Lehman, Johnson, Profumo, and Schwemberger, where they posit that you can, if you stabilize them by giving them a dark charge or something like that, then you might do direct detection of these fairly heavy particles passing through the Earth using paleo detectors or something like that.
Okay, thanks. And well, it's been proposed that dark matter could have killed the dinosaurs, but maybe primordial black holes can go around not assassinating individual people.
So we're past 5 p.m. So maybe Archel can stop recording now, and then people can kind of slowly evaporate away.